Hi students, now let us consider the module 3. So here in module 3 we already know the topic related to Fourier transforms and also difference equations and Z transforms. So we have successfully considered problems, properties, etc. for Z transforms and its applications, which is also known as difference equation or solving the difference equations. Now we have successfully completed the problems related to Fourier transforms. So in Fourier transforms, we have learned what do you mean by Fourier transform and its inverse Fourier transforms, properties associated with the same, and also a few problems related to the topic. Now we have to consider the next topic, which is called as Fourier sine and cosine transforms. So here first is we will know what do you mean by a Fourier sine and cosine transform, how to express the same in a mathematical way, which is known as a formula to represent the Fourier sine and cosine transforms, elementary functions and also its properties. Obviously, we are going to consider the properties directly as a statement without considering the proof and few problems related to the same. And also we will learn how to represent the inverse Fourier, cosine and sine transforms. Okay guys. So now first let us consider the definition of the required transforms. First we are going to write the definition of an infinite Fourier sine transform. So to define an infinite Fourier sine transformation, I need to have a real valued function f of x, which is defined for all positive values of x. Then mathematically the Fourier sine transformation of f of x denoted by f suffix s of u, or you can also represent the same as fs cap of u, also called as Fourier sine application on the real valued function f of x as integral 0 to infinity f of x sine ux dx. So when you observe the integrand here I have the term dx. So whenever I have the term dx, what does it represent? Integrate the function with respect to x. So x will be treated as a variable in this case, treating u as a parameter. Okay, since whenever you apply Fourier sine transformation on a real valued function f of x, the resultant will be in terms of the parameter u. You can also represent that by the expression as fs of f of x is equals to fs cap of u. You can either consider the representation as capital F suffix s of u or small f suffix s cap of u. Any representation will be considered according to our requirement and represents the Fourier sine transformation. Fine. So if this is our infinite Fourier sine transformation, what about its inverse? So what we do is we are going to apply inverse for the definition of the Fourier sine transformation, and it is given by the expression, observe guys here, f inverse of fs of u, or you can also represent the same as f inverse of fs cap of u is equals to 2 divided by pi integral 0 to infinity fs cap of u into sine ux dx, which will be in terms of a variable x. Means what? Whatever Fourier sine transformation expression you have obtained in terms of u, that should be substituted into the RHS, and then we are going to integrate the function with respect to the term or the parameter u in this case. And we have the term 2 by pi, the constant term 2 by pi associated with the definition, which we need to remember for the inverse Fourier sine transform. Okay. Now let us consider the definition of Fourier cosine transformation. So what is the definition? As usual, consider a real valued function f of x, which is defined for the positive values of x. Then its Fourier cosine transform represented by fc of u or fc cap of u is integral 0 to infinity f of x cos ux into dx. Or you can also simply represent the same as fc of f of x is equals to fc cap of u. Now what is its inverse Fourier cosine transform? Its inverse Fourier cosine transform therefore is given by the expression f of x is equals to 2 divided by pi integral 0 to infinity fc cap of u cos ux dx, or I can also write it as F inverse of Fc of u or F inverse of Fc cap of u. Okay, so this is the definition or the mathematical way of representing infinite Fourier sine, its inverse, infinite Fourier cosine transform and its inverse. Okay, so now we are going to consider few properties of infinite Fourier sine and cosine transform. So before we write down the properties, so let us consider some pre-assumptions. So if the Fourier sine transformation of f of x is denoted by fs cap of u and Fourier cosine transformation of f of x is denoted by fc cap of u, means what? Before you use the property, you should already know the Fourier sine transformation of the given real valued function, which will be in terms of u. Once you know them, then you can use the properties according to the requirement for the system. So, what is the first property? First property is called as linearity property. Since we have considered the linearity property in Laplace transform and also Z transforms, I think you guys can guess what can be the linearity property. So guys, let's see the statement of the linearity property here. So this is the linearity property. So what is that exactly? It is Fourier sine transformation of the constant c1 times of f of x plus c2 times of g of x can be written as, take the constant outside and apply the Fourier sine individually. That is what it means. So RHS will be c1 times of Fourier sine transformation of f of x plus c2 times of Fourier sine transformation of g of x. Similarly, if you apply the cosine transformation, the linearity property holds good. So this is the first and very most basic property whenever you consider any transformation, where obviously C1 and C2 are constants. What is the next property, guys? Now it is called as change of scale property or time scaling property. So here change of scale property means already I should know the Fourier sine transform of a real valued function f of x, which will be in terms of u. Then if you want to find the Fourier sine transformation of a function of the form f of ax, observe the scale over here, I mean the variable. So basically the variable is in terms of x, but you need to write the Fourier sine of a function where the variable or the scale is in terms of the form a into x. Then it is or it can be written as 1 by a times of Fourier sine transform of u divided by a. Now what do you mean by this property? That means consider the Fourier sine transformation of the function f of x, which we are going to denote by fs of u. Into that definition, replace u by u divided by a, and the expression is appended by 1 by a times. So that gives the Fourier sine transformation of the required function of the form f of ax. Similarly, we have the time scaling property for Fourier cosine transformation. So what is Fourier cosine transform of f of ax? It is given as 1 by a times of Fourier cosine transform of u divided by a. That means first find the Fourier cosine transformation of the function f of x, which is denoted as fc cap of u. Into the definition, replace u by u divided by a and append the expression by 1 by a. You are going to get the required change of scale property for the problem. Next, we are going to consider the next property. We call it as modulation property. So what is modulation property, guys? Here it is given as, observe. So I know the Fourier sine and Fourier cosine transformation of a real valued function f of x. But while solving problems, I will be in need of writing the Fourier sine and Fourier cosine transform of f of x times of cos ax. That means product of any real valued function with the cosine expression. Then it can be written as the average of Fourier sine transform of u plus a and u minus a. Similarly, if you want to find the Fourier sine transform of product of a real valued function f of x with a sine wave, or that is sine ax, then it is given as average of Fourier sine transform of u plus a and u minus a. Okay. Similarly, the same rule applies with Fourier cosine transformation. We call this as modulation property. So these are the basic properties of infinite Fourier sine and cosine transform, which we are going to consider while solving in the method of problems. Now guys, let us see the problems for Fourier sine and cosine transform. Since this is the first problem, we have considered a very simple problem and we are going to solve it. So the problem is of the kind, find Fourier sine and cosine transform of f of x, where the definition of f of x is supposed to be x in the interval 0 to 2 and the function is 0 in any other interval or any other domain or region. So what is the first step? I am going to find the Fourier sine transform. So we need to write the definition of the Fourier sine transform. So this is our definition. Fs cap of u is integral 0 to infinity f of x sine ux dx. First write down the definition, then substitute for f of x. Now to substitute for the f of x, I mean the definition of f of x according to the given problem, I have the interval to be considered because by the definition the limits or the interval is from 0 to infinity, but when I observe the given function, the function is defined only in the interval 0 to 2 and in all other region the function becomes 0. Fine. So what I am going to do, I am going to rewrite the interval. Now observe this guys. Here I have the interval as from 0 to infinity. I can rewrite this as 0 to 2 plus 2 to infinity. Now I am going to consider the definition. So from 0 to 2 the function f of x is x and in the other region, that is from 2 to infinity, the function is 0. So the definition of the infinite Fourier sine transform for the given problem will be written as, see, observe this, Fourier sine transform of u is equals to integral 0 to 2 f of x is x in the interval 0 to 2 sine ux dx. Fine. So what I have to do now? I have to now use either integration by parts or the Bernoulli's rule. And we already know that Bernoulli's rule gives us this expression or the solution expansion or quickly compared to the integration by parts method. So I am going to use the Bernoulli's rule. So what is the Bernoulli's rule? Consider the first and second term of the integrand. Fine. So first write the first term. Here first term is x, second term is sine ux. So I am going to write it as x into integration of the second term. So what is integration of sine ux with respect to x? It will be minus cos ux divided by the derivative of u into x with respect to x, which gives me u. And the limits are obviously x varies from 0 to 2. Minus sign by the Bernoulli's rule. Now consider the first term of the expression. Here first term is x. What is derivative of x with respect to x? It is 1. I am going to now consider the second term over here, which is minus cos ux divided by u. Now integrate minus cos ux. When I integrate minus cos ux, minus 1 by u will be considered as a constant at this moment. Integral of cos ux gives me sin ux divided by u. So finally it gives us the expression of the form minus sin ux divided by u square. And the limits are x is equals to 0 to 2. Okay. So what is the next step now? I have to substitute the upper limit and the lower limit for the variable x. So before we substitute, let us take the constant term outside and then do the substitution. So from the first term, minus 1 by u is treated as a constant. So I am going to write the expression as x into cos ux. Means we are grouping the terms which has the variable x so that it makes us easy for the substitution of the limits. Then observe the second term. Minus into minus is plus. 1 by u squared is treated as a constant at this instance. So take 1 by u squared outside. So we are left with sin ux where x varies from 0 to 2. Now substitute for the limit. When I substitute the limit for x, it is minus 1 by 2 times of, I am going to substitute the upper limit first, which is 2 in this case. So it will be 2 into cos 2u minus, when I substitute 0, cos 0 is 1 and I have the term x. So 0 into 1 gives me 0. This will be the value of the expression when I substitute the lower upper limit and then the lower limit. Now similarly substitute for x in the second term. So it will be 1 by u squared into, when I substitute x as 2, I am going to get it as sine 2u minus substitute x as 0, it will be sine 0. We know that sine 0 is 0, so I am going to write it down as 0. Now we are going to rewrite the expression by taking u squared as a common factor. Okay. So when I write the expression by taking u squared as a common factor, the expression will be, I have u squared in the denominator, sine 2u minus 2 times of u cos 2u. So this is the Fourier sine transformation of the function f of x given by the definition x in the interval 0 to 2 and 0 in any other region. Okay. So now observe the expression over here. See, we have RHS where we have only the constants involved and the parameter u. Hence, we are going to represent the expression obtained after applying the Fourier sine transformation as fs cap of u. This completes the first part of the problem. Okay. Now, let us consider the second part. What is the second part here? I have to find the Fourier cosine transform. So as usual, first write down the definition. Fourier cosine transformation of the function f of x denoted as fc cap of u is given by the expression integral 0 to infinity f of x cos ux dx. Now we are going to substitute the definition of f of x. So rewrite the interval. The interval now 0 to infinity will be considered as 0 to 2 plus 2 to infinity. So when I substitute the same, the expression becomes fc cap of u is equals to integral 0 to 2 f of x is x cos ux dx. As usual, use the Bernoulli's rule. Here I am treating x as the first term and cos ux as the second term. So by the Bernoulli's rule, first term I should consider as it is x times of the integral of cos ux. What is the integral of cos ux? Sin ux divided by u. And the limits are where x varies from 0 to 2. Minus sign by the Bernoulli's rule. Differentiation of x with respect to x. Derivative of x is 1 and I have to find the integration of sin ux by u. We know that integral of sin ux by u is minus cos ux divided by derivative of ux. Derivative of ux gives us u squared and the limits are x varies from 0 to 2. Now take the constant term outside and rewrite the expression. So it will be of the form 1 by u times of x sin ux plus 1 by u squared cos ux with the limits x varies from 0 to 2. Fine. So now let us see what can be the value. When I substitute x as 0, sin 0 is 0. When I substitute x as 0, cos 0 is 1. So first let us substitute the upper limit. Therefore, the expression is now fc cap of u is equals to 1 by u times of, when I substitute x as 2, it will be 2 sin 2u minus when I substitute x as 0, I am getting the expressional value as 0 plus 1 by u squared times of cos 2u minus cos 0. So it is 1 because cos 0 is 1. Now simplify by taking LCM. So here I am taking u squared as LCM. Therefore, the expression is now 2u sin 2u plus cos 2u minus 1 divided by u squared. So this is the second step of the problem which uses the Fourier cosine transformation of the function f of x. Now guys, let's consider the next problem. Here I have to find the Fourier sine and cosine transform of a function f of x given by the definition e to the power minus ax where a is a positive value. So this will be the first part. So what are we going to do in the first part? We are going to consider f of x. We are going to consider the definition of Fourier sine transformation, substitute, integrate and simplify. In this again then we are going to consider cosine transformation formula, substitute and integrate and simplify, which uses the first part. Now what is the second part of the problem? Observe the problem here. Hence deduce that the Fourier cosine transform of f of x. So I have to find with the help of the obtained Fourier cosine transform of f of x, which is e power minus ax. I have to find the Fourier cosine transformation of a function of the form x into e power of ax minus ax. And also the third part is with the help of the obtained Fourier cosine transformation from the previous step, I have to find the value of the definite integral cos lambda x by x square plus a square dx where the limits are from 0 to infinity. So totally three stages or three steps should be considered to solve the problem. So what is the first step? Find the Fourier sine and cosine transformation, for which we are going to write the formula. So the Fourier sine transformation of the function f of x denoted as fs cap of u is integral 0 to infinity f of x sine ux. Write down the formula. Now substitute for f of x. So what is f of x here? It is e power of minus ax where a is a positive value. So obviously the limits will be considered as 0 to infinity. Now to evaluate this integral, we have a standard formula which is given as integral 0 to infinity e power ax sine bx dx is e power of ax by a square plus b square times of a sine bx minus b cos bx. So when I compare the LHS of the formula with the RHS of the previous step, I have to substitute a as minus a, b as u and write down the RHS. So therefore, the Fourier sine transformation will be now e to the power minus ax by minus a square gives me a square plus u square. So I am replacing a with minus a into the formula. So the expression will be now minus a sine ux minus u cos ux. Now I have to substitute for the variable x. So we are going to take common factor. The constant term 1 by a square plus u square outside. Then rewrite the expression. So when I rewrite the expression here, it is of the form 1 divided by a square plus u square times of e to the power minus ax into minus a sine ux minus of e to the power minus ax into u cos ux with the limits x varies from 0 to infinity. Now I am going to substitute the upper limit. So let us write down what can be the values of the expression when you substitute the limits. So here when you substitute x as infinity, we have the term involved e power of minus ax. So what is the value of e power of minus ax when x is infinity? It is 0 because we know that e power minus infinity is 0. Then when you substitute x as 0, we get the expression e power minus ax to be as e power 0. So e power 0 is 1. Therefore, we are going to substitute 1 when we substitute x as 0 for the expression e power minus ax. And also, we know that sine 0 is 0 and cos 0 is 1. Now, we are going to substitute these terms into the previous expression. So, it will be now Fourier sine transform of u is equals to 1 divided by a square plus u squared times of, I am going to substitute e power minus infinity, x as infinity, therefore the first term will be 0. Therefore 0 minus sign before I substitute the lower limit, then substitute x is equals to 0. When I substitute x as 0, e power 0 is 1 and sine 0 is 0. Therefore, the first term will become 0 after substituting the limits for the variable x. Now, let us substitute for the second term. It is when I substitute x as infinity for exponential, it will be 0 because e power minus infinity is 0. Therefore, it is 0 minus of u times of cos 0. So, cos 0 is 1. Hence, I am left with minus u for the second term. Now let us simplify this. We know that I have minus sign. The product of minus and minus u gives me positive. Therefore, the Fourier sine transformation of the given function is u divided by a square plus u square. Now we are going to write the Fourier cosine transformation of the function f of x. As usual, first write down the formula. Therefore, the Fourier cosine transformation of f of x denoted by fc cap of u is integral 0 to infinity f of x cos ux into dx. Now substitute for f of x. f of x is e to the power minus ax. Call this as equation 1. And we already know the formula as integral of e power ax cos bx dx as e power of ax by a square plus b square times of a cos bx plus b sin bx. So here I have to replace a with minus a and b with u and simplify. Okay. So therefore the Fourier cosine transformation is now, after using the formula, becomes e power of minus ax divided by a square plus u square minus a cos ux plus u sin ux with the limits x is equals to 0 to infinity. Now take out the constant terms and regroup the terms which has the variable x so that it will help us to substitute the limits. Therefore, now here 1 by a square plus u squared is considered as a constant, and I have minus a for the first term times of e to the power minus ax cos ux plus e power minus ax sin ux into u, and the limits are x varies from 0 to infinity. Now as x tends to infinity, we have the term e power minus ax. Therefore, e power minus infinity is 0. And when as x tends to 0, e power 0 is 1. And we have the sine and cosine terms. Therefore, cos 0 is also 1. And I have sine 0 as 0. These values will be substituted into the previous expression for further simplification. Therefore, Fourier cosine transformation is now 1 divided by a square plus u square times of minus a into e power minus infinity is 0. 0 into any value is 0. So I have the term 0 minus sign before I substitute the lower limit, cos 0 because x is equals to 0 is the lower limit. So cos 0 is 1. Therefore, the first term expression after substituting the limits will be 0 minus 1 times of minus a. Similarly, what can be the second term? Plus u into e power minus infinity is 0. I have, therefore the value will be 0. Minus sign 0 is 0. Hence we have it as 0. Okay. So if I simplify and rewrite the expression, the Fourier cosine transformation of the function e power of minus ax denoted by fc cap of u is a divided by a square plus u square. Okay. So now this completes the first step or the first stage. Call the obtained expression as equation 2. Why? Because with the help of this expression, I have to find the Fourier cosine transformation of x times of e power of minus ax. So I am going to consider the equation 1 here. Equation 1 is integral e power minus ax cos ux dx with the limits 0 to infinity, which is equals to fc cap of u. From equation 2, what is fc cap of u? That is a Fourier cosine transformation. It is nothing but a divided by a square plus u square. So this is what we are going to get. Fine. Now what we are going to do is, we know that Fourier cosine transformation of the f of x is denoted as fc cap of u, with the help of which we have written the expression, okay, which is given as integral 0 to infinity e power minus ax cos ux dx is equals to a divided by a square plus u square, which is nothing but the Fourier cosine transformation of e power of minus ax. Now we are going to differentiate with respect to a. So when we are differentiating with respect to a, x will be treated and u will be treated as constants. So what are we going to get? LHS is d by dA of the integral is equals to the derivative of the RHS with respect to a. Now RHS, to integrate RHS, we are going to use the, differentiate RHS, we are going to use the quotient rule, and the term, the general derivative d by dA becomes partial derivative when we bring it within the integral sign. We call this as the rule of integration by the rule of differentiation under integration by the Leibniz rule. Therefore, I am going to differentiate the expression, I mean the integrand with respect to a. So, when I observe the expression, the integrand e power minus ax cos ux, I have the term e power minus ax which will be treated as a variable, cos ux will be treated as a constant at this stage. Now RHS, we have used the quotient rule. So quotient rule, according to the quotient rule, I have it as a square plus u square the whole square, I mean the denominator square. Now consider the first term of the numerator. So the first term of numerator will be, write down the denominator a square plus u square, then differentiate the numerator with respect to a. Derivative of a with respect to a is 1 minus, I am going to write down the numerator a into differentiation of the denominator gives me 2 into a. So when I simplify, it gives me minus 2a square. Simplify this further, you will get it as a square plus u square minus of 2a squared in the RHS. Now derivative of e power minus ax with respect to a gives me minus x e power of minus ax. So here minus 2a square simplifies with a square. So we are left with u squared minus a square divided by a square plus u square the whole square. So what can be the next step now? Multiply the expression with negative sign. So we are left with integral 0 to infinity x e power minus ax cos ux dx is equals to a square minus u square divided by a square plus u square the whole square. Now let us consider the expression. So observe guys, here I have it as integral 0 to infinity e power minus ax cos ux dx. So when I have this function e power minus ax is called as f of x. So according to this integral, this is nothing but the Fourier cosine transform of e power of minus ax. So if I consider the same concept with respect to the integral what we have right now, I have the integral as integral 0 to infinity x e power minus ax cos ux into dx, which implies by the definition of Fourier cosine transform that this integral represents the Fourier cosine transform of the function x e power minus ax. This is by the definition of the Fourier cosine transformation. Therefore, what is Fourier cosine of x e power of minus ax? Which is nothing but a square minus u square divided by a square plus u square the whole square. So this completes the second stage. So here see, with the help of the Fourier cosine transform of e power of minus ax, we have obtained the Fourier cosine transform of x e power of minus ax. Now we have to move on to the third step or the third stage. So in the third stage, I have to evaluate the definite integral of the form cos lambda x by x square plus a square the whole square. So to do that, we are going to consider the Fourier cosine of e power of minus ax, which we have obtained for the current problem as a by a square plus u square, which is denoted as fc cap of u. Okay. Fine. Now consider the formula for inverse Fourier cosine transform. So the inverse Fourier cosine transform denoted by f of x is given as 2 divided by pi integral 0 to infinity fc cap of u cos ux du. Now we are going to substitute for the Fourier cosine transform. So we know that from the previous steps, Fourier cosine transformation is given by the expression a by a square plus u square. Okay. So this is by the definition. We are going to substitute here a by a square plus u square. So when I substitute the same, the Fourier inverse cosine transform will be now f of x is equals to 2 divided by pi integral 0 to infinity a divided by a square plus u squared into cos ux dx. Okay. So what we are going to do is now, we are going to now compare the integral with the required expression to be obtained and we will simplify accordingly. Okay. So for that substitute f of x. What is f of x? E power minus ax. Guys. Now we are going to bring the term e power minus ax and 2 divided by pi to the other side. So the expression will be left for the integral cos ux by a square plus u square du with the limit 0 to infinity as pi divided by 2a e power minus ax. Just we have rearranged the terms over here. Okay. So now when I compare this LHS of the expression with the integral to be evaluated, fine. So it implies that I have to rewrite the expressions for u and a etc. So what I do, I am going to now write the change the variable x to lambda and also u to x. First I am going to write x as lambda. So the expression will be cos u into lambda and RHS will be e power of minus a into lambda. Then replace u to x. So it gives us integral 0 to infinity cos lambda x by a square plus x squared into du is equals to pi by 2a times of e power of minus a lambda. So the value of the integral as required by the problem is also obtained with the help of the Fourier cosine and sine transform. Hence the value of the